Our last topic in one-dimensional motion is free fall. So for the situations with free fall, our kinematic equations are exactly the same ones. The only thing is that we're adding this notation that we're specifically talking about the y direction. So here, our velocity is in the y direction, our initial velocity is in the y direction, and now our acceleration is not just any acceleration, but gravity. Over here, same thing. Our displacement is no longer just a displacement in the x-axis. Now it's along the y-axis. So again, it's just giving us a little bit more information that our displacements along the y or up and down now, that our velocity is in the y, and that our acceleration, again, is due to gravity. Same thing here, here, and here. So we are using the exact same kinematic equations, but now we've just transferred them over so that it looks like something we can apply to situations where something is moving up or down. So again, just to tell you a little bit more about our acceleration, it is the acceleration due to gravity. This has a magnitude of 9.8 meters per second squared. Again, magnitude just talks about the numerical value. So it does have a value of 9.8 meters per second squared, but again, that negative is telling us that it is always acting downward. Okay, this always acts downward. Also, we're going to assume that acceleration is always constant. Now, these situations are assuming that we're happening in a vacuum. What that means is we're happening in an area without any air resistance. Okay, we are eventually going to talk about situations where we have air resistance, but then we can't use our kinematic equations because, again, our kinematic equations can only be used when acceleration is constant. When we have air resistance, our acceleration is no longer constant. So remember that a freely falling object is any object moving freely under the influence of gravity alone. Again, we are ignoring the effects of air resistance in this case. It also doesn't depend upon the initial motion of the object. So different situations we're going to look at is something that is just being let go or released from rest, something that is thrown with some velocity downward, and something that is thrown with some velocity upward. So we dealt with free fall examples last year, but normally something was only going up or only coming down. But now we can talk about situations where if I toss something upwards, it can reach its highest peak and then come down and even fall beyond where I started. So I want you to take a minute to look at all these different situations happening over here. So I have a position A here, a position B up here, a position C, and a position D, and then down here we have a position A. The next slide is going to zoom into these sections a little bit more, so I just want you to kind of see what's happening, all the different pieces. So here at position A, we are starting with an initial position of 0 meters. This is also telling us where we begin. Again, when time is equal to 0 is when we begin. We have a velocity in the y direction at point A of 20 meters per second. That means I've given it an initial velocity upward of 20 meters per second. Okay. Again, the fact that it's positive here tells us that we're moving upward. Also, at this point, like at all points, our acceleration due to gravity will always be negative 9.8. At position B, we have reached the top of our path. So here, it's telling us we've gone 20.4 meters. That means we've moved up 20.4 meters. It took 2.04 meters to get there. And at the highest point, we have stopped. So this is where our 0 velocity comes from. Again, even though we have come to a stop, and this is probably one of the hardest things to remember, is that if we come to a stop, we still have an acceleration of negative 9.8. This is true at every single point of our path. We will always have a constant negative 9.8, even if we have come to a stop. Now over here at position C, it's telling you that we are 4.08 seconds away from when we started. So this is 4.08 seconds later. Our displacement is 0. That means we have ended up exactly where we began. Okay? So anytime that you start and end at the same position, your change in position is equal to 0. Here we have a negative velocity. Again, what that tells us is that we are moving downward. So negative velocity means we're moving downward. And as always, an acceleration in the y direction is going to be negative 9.8 meters per second squared. Here we're looking at point D. So point D is now beyond where we started. So our little guy is over here. Our little guy is over here. Or somewhere over here. This is where he tossed the ball upward. The ball reached its highest point. Now it passed its original position, and now it has moved beyond that. So this is happening 5 seconds after we tossed it. We are now a displacement of negative 22.5 meters from, again, where we started. That means we are 22.5 meters below where we started. Again, we have a negative right here. This tells us that we are moving downward. And as always, negative 9.8 meters per second is our acceleration at every single point. And at point E, which is our last point here. This is happening 5.83 seconds after we started. Now we are negative 50 meters. So again, this is our displacement. We are 50 meters below where this was tossed. Where we started. Okay. And negative tells us we have been moving in the negative direction for quite a while now. Anytime that we're falling or going downward, we are moving in a negative direction. And as always, and I can't stress this enough, this always comes up as a multiple choice question on the AP exam, asking what is your acceleration at the highest point, or what is your acceleration at some point. It's meant to confuse you because sometimes students assume that if I stopped, then I have no acceleration, but that's not true. Acceleration is always negative 9.8 meters per second squared. So now to finish up with an example. Here, we have a student tosses her keys vertically to a friend in a window 4 meters above. The keys are caught 1.5 seconds later. With what initial velocity were the keys tossed? So, starting with our kinematic equations, or actually, starting with the information. We know that they are caught 4 meters above where you are, that it is caught 1.5 seconds after you tossed it, and what we're trying to solve for is initial velocity. So remember that with kinematic equations, you have to have at least 3 pieces of information, so 3 known, I just spelled known, 3 known pieces, 1 unknown. Okay, good. 3 known pieces of information and 1 unknown piece of information. So right now, I only have 3 pieces or 2 pieces of known information. That means I need at least 1 more known piece of information. So with free fall problems, if you're missing something, double check that it isn't gravity that you're missing. And in this case, it is. So 4 meters above. This is our displacement in the y direction. 1.5 seconds later, this is our change in time. Again, we know gravity. This is our acceleration in the y direction. And what we're trying to solve for is our initial velocity. So, the only equation that has all 4 pieces is our first kinematic equation, which is delta y is equal to v naught t plus 1/2 a t squared. Again, you can specify this is acceleration in the y direction, or you could have just called this g to begin with. So what I'm trying to do is solve for initial velocity. So even though you can do all of these problems in your head, it is going to be very important that you show all of your steps. Again, you will get more credit showing your work rather than just giving an answer. So to get velocity by itself, I want to move this entire piece all together. And some of you had questions on this when we did the math review. Move it all to the other side. So it looks like this is step 1, this is step 2. Now our equation looks like this. Negative 1/2 g t squared is equal to v naught t. Again, next step, I'm trying to solve for initial velocity. So I divide by time, divide by time. And I have every single piece on the left-hand side. So just clean it up a little. I have all these pieces. My displacement was 4 meters. I have 1/2 negative 9.8 meters per second squared. Remember to square the time here. All divided by time again. Okay? And always double check your units work out. Here, these seconds squareds would cancel. And I have meters combining with meters, ending with over seconds. So our final answer is 10.02 meters per second. 10 is fine as well. So this is our initial velocity. The second part says, what was the velocity of the keys just before they were caught? So what it's asking for is to solve for final velocity. We can't assume that the final velocity would be 0 because it didn't reach 0 by itself. It was forced to come to 0 because you caught it. Okay? Had you not caught it, it doesn't mean that it would have reached 0 at that point. So we cannot assume that our final velocity is equal to 0. And this is really important, a very, again, common problem. So if we're trying to solve for final velocity, well, I can use final velocity. Oh, we're going to use the AP notation now. Final velocity is initial velocity plus acceleration times time. Because we are talking about the y direction, I can specify this is y, and this is g. So this becomes 10, I'll just put 0.2, negative 9.8 times 1.5 seconds. Again, my units work out, so that's good. You should get a final velocity of negative 4.68 meters per second. Another way to say that, or I'm sorry, negative 4.7 would have been fine too. Now, after you solve a problem, we want to look and analyze what's going on. The fact that we got a negative here tells us that these keys were caught on their way down. So they weren't caught on their way up. Or we would have gotten a final velocity of a positive number. These keys were caught on the way down. And again, I know that because of this negative number. And we're done.